Thanks for joining us today for Encrypted Traffic Analysis, Hype versus Reality from the Trenches. My name is Bill Gardner, Technical Marketing Lead at Awake Security, and I'm joined by Troy Kent, one of the top threat researchers from Awake Labs. Troy's presentation today is a follow-on to last week's presentation by Gary Gollum on the topic of using encrypted traffic analysis for threat detection and hunting. Troy will be exploring this topic in depth today, so if you have any questions, please type them into the Zoom Q&A window, and we'll try and get answers for you at the end of the session. So with that, I will turn it over to Troy.
All right. Hello, everybody, and welcome. Thank you for joining us today. I hope everyone's doing well as can be expected. Hashtag 2020. Today we'll be talking about something that I very much enjoy and have been sort of obsessed with over the past few years. So this is should be hopefully a pretty interesting and eye-opening presentation. So what we're going to talk about today, as a follow-on to last week, what Gary was talking about, is the nature of TLS traffic. TLS, well, encrypted traffic, right? Sort of redundant. We're going to look at encrypted traffic analysis options. We're going to look at making those options work for actual detection, find bad things, weed out good things, the things that we want to do. And then we'll be putting them to work in real examples, such as proxy bypass attempts, AppleScript with the Cocoa library, scripting identification, detecting the JA3 evasion techniques, and then also Chrome extension identification. So looking at traffic and deciding what is a Chrome extension and what is just normal Chrome traffic. So first, a brief history of TLS. As you may or may not know, it started off with SSL and then moved to TLS. In fact, it was a recent version of Wireshark that finally changed the field name from SSL to TLS. And then it went from TLS 1.0 to 1.2 to finally recently 1.3. And here, one second. Okay. And in addition to just the TLS version upgrading from SSL to TLS, after it became TLS, they started adding a lot of extensions to increase the efficiency of the protocol or to add additional capabilities that weren't in previous versions. And rather than create a new version every time, they started to come up with these extensions. I think that was one of the main reasons why they moved from SSL to TLS in the first place. And what that looks like, if you see on the left-hand side, there's a list of just the first 40 extensions, which there are very many more than that, and there's up to like 63,000 potential ones. And each of them do something a little bit different. Some of them have value. Some of them are just either there or not there to let the server know whether or not it supports something, et cetera. In addition to adding extensions as time goes on, Cipher suites are added, Cipher suites are taken away, more Cipher suites are added. So when we get new Cipher suites, more secure Cipher suites, we add those. When we have a Cipher suite that's vulnerable to something or outdated, we remove it, et cetera. Something that's relevant to TLS fingerprinting and encrypted traffic analysis we'll be talking about is that these RFCs that we're looking at are specs, essentially suggestions that describe how to do something. And then those specs are implemented by several possible pieces of software. Oftentimes you'll see the specs are, the RFCs are written by some particular company or group that is writing the first implementation, but then that is taken and implemented by other places. And you'll see how that's relevant soon. But basically what that translates into is that different operating systems, different browsers, and different applications are using different implementations of these protocols and of these extensions. For example, there are probably 4 most common SSL libraries. We're looking at OpenSSL, Boring SSL for Chrome, NSS something for Firefox, S-Channel, I guess 5, right? S-Channel for Windows, and Apple Secure Transport for Apple. And each of those They both, have they don't update at the same time. Of course, they're on different update schedules. They may add and subtract different Cipher suites depending on what they want to support. They may add and subtract different extensions depending on what they support. And they may also expose different amounts of Cipher suites and extensions to the software developer that's implementing their library. Because in addition to those low-level libraries, there are, software and libraries built on top of those that use those libraries, and then so you can make different decisions about what you want to use. For example, if you're writing the requests library in Python, then I think that uses OpenSSL. So you're going to make decisions using the requests library as the creator of that library about what extensions you want to implement, etc. But again, the end result is just that we have all of these different softwares, all of these different operating systems, browsers, and apps with a different collection of extensions, Cipher suites, versions, etc. Also, fun note, if you're going to read as many RFCs as I have over the last few years, you'll definitely want to get some computer glasses because it will start to wear and tear on your eyes. So not all encrypted traffic is encrypted. Gary definitely mentioned this last week, but just to show you again, here is an example TLS 1.2 packet and Wireshark. And you can see, so this is a client hello, right? So it's advertising to the server the things that it supports, including the type of encryption that it supports, the extensions that it supports, protocols, etc. All that information is in plain text, not encrypted, right? So we can still look at it. Important to note that, again, I think Gary mentioned this, but TLS 1.3 is no different. Here's an example TLS 1.3 packet. You can still see the AOPN values, the extension values. The Cipher suites are not broken out, but they are also in plain text still. So everything is largely the same. This one does actually have an encrypted server name extension. So that is technically encrypted in this example, although we'll go more to that or into that in a second. So TLS 1.3. This is, one of the more important things that I think we need to talk about when talking about encrypted traffic analysis. There are a lot of blog posts, a lot of articles and things like that are talking about TLS 1.3 in a very doom and gloom way with respect to detection, or maybe they're just talking about encryption as doom and gloom with respect to detection. Oftentimes you'll see this kind of thing being pushed by vendors who are telling you to decrypt traffic wholesale. So you can see why they would want to kind of spread that myth. But I wanted to show you that, what those myths are that are being propagated fairly ubiquitously, and examples and exactly why they are myths. So the first one is the server name is encrypted. So the last thing, the screenshot that you saw was an example of an encrypted SNI packet looking at it in Wireshark. That was captured by using basically the ESNI tester with Firefox and Cloudflare. And it's important to note that Cloudflare is the group that is implementing ESNI and also ECH, which we'll talk about in a second. And it has been seen in the wild, ESNI has, mostly, I believe, with Firefox. I think it's technically possible to turn it on with Chrome, and you might see it in Cloudflare, but it's not ubiquitously, it's not very common, but it is happening in the wild. But something to point out is that it did exist in a draft, in an RFC draft, ESNI did, but that was superseded. It's actually the same RFC draft. It's still called ESNI, I think, or you can see in the Git history where they changed the name. But it's been discarded in favor of encrypted client hello, which seems to be indicative that going forward, what we're going to do, or at least what Cloudflare is going to do, and then what presumably will be picked up by everybody else, is going to be encrypted client hello instead of encrypted server name extension. And as I said, there were implementations, or there currently are, but it doesn't appear to be adopted, at least in a large sense, outside of Cloudflare. And you have to think, like, if you want this to be adopted widely, that means that Apache has to pick it up, Nginx has to pick it up, or I guess OpenSSL or Nginx implementation of that. But all of the libraries, Caddy, for example, they have to implement this in order for it to work on the server side. Client hello. is encrypted. So that's another myth. I will literally read blog posts that say, well, we can't use TLS fingerprinting because the client hello is now encrypted, which is just not true. Again, this ECH, as they call it, used to be called ECHO. This is currently in draft. And I've yet to see it in the wild. I'm constantly looking for it in the wild because I want to know what it actually looks like when it's implemented. Although I do expect it to show up on Cloudflare and in Firefox first, as is tradition with these things, apparently. Which leads us to the next myth, which this is usually followed up directly after client hello is encrypted. It breaks TLS fingerprinting. So see above. Right now, so let's say ESNI, right? So does ESNI break TLS fingerprinting? Well, no, because everything else is still in plain text. So we can potentially still identify the client. There are other ways to identify the destination, depending on whether it's a CDN or something like that, or cloud hosting that might create some issues with destination identification. But again, those are not general problems. Those are sort of specific problems for specific cases. And again, that's not even what I expect to see going forward. What I expect to see going forward is encrypted client hello, which again is not in the wild currently that I have seen. So if you see someone saying that it is currently breaking TLS fingerprinting, that's not true. Okay, so then some people might say, well, when it is adopted, when ECH is adopted, it will break TLS. And next slide, yep. So let's talk about what we know about TLS 1.3 and whether it will break it when when ECH is implemented. So Gary mentioned this last week as well, and when he did, I silently clapped to myself. Without ECH, TLS 1.3 actually adds more identifying information. One easy example is the addition of the supported versions extension. So that's essentially like the way that they've made 1.3 work while kind of looking like 1.2 to middle boxes and other things to kind of create backwards compatibility with those things, is they just added an additional extension that says, hey, I support these versions, including TLS 1.3. And then it will go forward potentially with the TLS 1.3 handshake and the TLS 1.3 communication back and forth. But the fact that the supporting versions extension is there is identifying information. I think it was last week, Gary and I were looking at something, and we were talking about what it should be based off of the TLS fields, and I was immediately able to say, all right, look, there's no supported versions extension, so I know that all up-to-date current browsers have that extension, and they use that extension because they all support TLS 1.3 and they advertise it. And so knowing that it's not there gives us a good indication that it's probably not a browser. So again, just adding that, just the fact that it is TLS 1.3 adds more identifying information. And that's not the only extension that's been added that's specific to TLS 1.3. Some of them, just them being there is indicative of potentially a different client, or perhaps they have useful information. Some of them actually have like differing values, hash algorithms, things like that, that you can use to identify one or differentiate one client from another. Another thing to know is that it requires adoption by the client and the server. So if we're talking about encrypted client hello, that means that we have a client that supports it and we have a server that supports it, and it works throughout the entire process. Otherwise, it'll fall back and not use that, which means that we'll still get the plain text field information. And something that's interesting about that is that if you're looking at the network holistically, then even if it works in one case but does not work in another case for that same application on that same device or on a different device, then you may be able to pick up that context elsewhere in the network and then figure out, identify what it is you're looking at based off of the destination that it shares or something like that. Another thing to point out, this is kind of just like fun to know information from reading through the RFC, is that not all extensions are required to be encrypted. There's a little clause in there that says basically there are times when there are extensions that are long that you may not want to encrypt, right? So that means that if people choose to implement it that way, that there will be extensions potentially on the outside because they're long. There could be extensions on the outside of the encrypted client hello just because of that's how the implementation works. So we'll have to see. And I just wanted, it could be that means nothing at all. It's something that I noticed and I was like, all right, cool, we're going to keep an eye out for this. But at the end of the day, Once it's in the wild, which again, it is not, we'll have to see what identifying information is in the end result, and then we can make real world reactions to that. And like, for example, one thing is the public key has to be shared. So in order to encrypt this client hello, there still needs to be some sort of communication between the server and the client so that they both know how to encrypt that client hello and send it to each other and then decrypt it on the other end. Currently in the draft, the way to do that is asymmetric encryption, where they're sharing a public key. My assumption is that we could potentially use that public key to identify something about the destination. I don't exactly know what yet. We'll just have to see what it looks like in implementation. But again, the reality of the situation is that it's not magic. There has to be some sort of communication that's indicative of something. And so we'll figure out what it is. So currently, what are your TLS fingerprinting options? So now you're convinced that we shouldn't just throw away TLS fingerprinting because at the very least, we've got a runway and there's no reason to not implement something that's going to help us detect things, even if worst case scenario in terms of TLS fingerprinting occurs, right? So right now, your two options, or at least the two options that I looked into, are JA3, which is by far the most popular, if not synonymous at this point with TLS fingerprinting, and Mercury, which was formerly Cisco Joy, which is something that they created to fingerprint a number of protocols and kind of be a traffic aggregator from what I understand. So first we'll talk about JA3, which I have talked about in the past, but just as a refresher course, basically what it does is it takes some of those fields that we were just talking about and it hashes them. So it takes the extensions, so the ones that are there, it takes the version, inner version, outer version. It takes some of the extension values, but the same ones every time, and it turns it into an MD5 hash. Of course, that hash is easy to store and share. So if I hash some traffic, some TLS traffic on my network, and I say, hey, this is bad, I can share it with Gary, and he can run it on his network. I act as like we have different networks. And say, okay, well, now I found this bad thing that Troy found. But one of the issues is that by hashing, you do lose a lot of the context. I can share the hash with him, but he doesn't know what the ALPN values were. He doesn't know, basically anything, whether the grease values were there, which tells you whether or not it was using boring SSL, essentially. He doesn't know what the destination was unless I told him. He doesn't know whether the supported versions field or extension was there. And so whether it was TLS 1.3 or what, he doesn't know what version at all it was. So, all of that context and more is lost by me just sharing a hash. Something that I pointed out before, which is definitely relevant when hashing a bunch of stuff, is some of the fields are conditional. So the same client can choose to send one extension during one session and choose not to send it in another, but it's still the same client. And there's several reasons for that. One of them I'll go into later is cache. And another one is just what the library decides to do. For example, a library, some libraries, if you send a request with a server name in that request, it will include the server name extension, which is extension 0, which is something that is hashed, not the value, but the fact that the 0 is there, by JA3. And so excluding it would change the hash, right? Well, if you send a request from that same library and don't include the domain, so you just send it directly to an IP address, it doesn't do a DNS lookup or anything, it does not include that SNI extension. So same client, or at least same library, so same client using that library, but the hash is going to be different. And of course, there are other extensions that are like that, not just the server name. Other libraries, however, you can send an IP and they will include the IP in the SNI. Some libraries, if you send it straight to an IP, will include the SNI extension, but it'll be blank. So again, this goes back to different software, different libraries implementing things differently. But what the end result is of that is that we have JA3 values that are either different, like we'll have like 5 different JA3 values that are for the same client, same version, same everything. And then we'll have JA3 values that are the same, that are actually different clients, which happens a lot with system level processes and scripts and things like that. And again, what that means for us is that it's not that useful in a plug and play way. And so one of the things that I find surprising is when I read blog posts and articles and things that say, hey, so-and-so is supporting, or they do encrypted traffic analysis, or we do encrypted traffic analysis. But when you read deeper, it just says, at least from what I can tell, it just implies, or some of the webinars I've seen as well, where they just explicitly state, like, we implement JA3, you've got these hashes, you can search for them. But it's important to know that searching for a JA3 hash is nothing like searching for like a file hash, for example. Just because the hash is the same doesn't mean, it's not like going to VirusTotal and seeing an emotet hash and being like, oh, well, this binary is obviously emotet. It would be very weird to have a hash collision on this, right? This benign file. But that's just not how it works in JA3. And I think there's sort of an implication in the industry sometimes that it does work the same, and it doesn't. So since the last time I talked about JA3, there has been an open database that was created, but there's some issues with that as well, which we can get around in several ways. But just to show you, so this is what it looks like. You can drop in a hash. It will tell you the user agents for that hash. And the way it collects these based off of visitors to this site, potentially other sites as well. I imagine there's several nodes. And then it marries together the user agent that it saw for whatever visited it in the unencrypted traffic, obviously, and then the TLS fingerprint as well. And so we can see here, a bunch of user agents that look like browsers probably. There's also comments from the community. One says Chrome on Linux, Electron, which is the boring SSL, is the Chromium like thing that Slack and Discord and all that stuff is built off of, which makes it very similar to Chrome. Vivaldi, I'm not sure what that is. But the interesting thing is that this was actually Chrome on OS X. Does that matter in a threat situation? Nah, not really. But it is important to know that, again, it's not a one-for-one thing. You're not going to necessarily put in a hash here and get the exact thing that you're looking for. And so the next thing we'll talk about is Mercury, which certainly is a step up from JA3. For one, it keeps all of the data, it collects all of the data. So all of the extensions, their values, et cetera, and it keeps it around, which is very important. Or at least certainly better than hashing it and getting rid of all of it. It does process analysis, which can be good if it's accurate. And I think, I couldn't find this on the Mercury GitHub, but I believe I remember it from back when it was Joy, where they said that they were using some sort of host-based agent on the network that they were monitoring, and then cross-referencing the host-based information with the network so they could say, for sure, this is exactly this thing. And it also fingerprints a number of protocols, not just TLS, but DTLS, SSH, HTTP, TCP. It does more than just TLS, which is obviously different than JA3. It keeps the context of the traffic. So again, that is a net gain, but it's not included in the context of the network, which, just want to make the statement, it's not the author's intent, I don't think. It is a network traffic collector and fingerprinter. It's not meant to make, it's not meant to tie together devices or look at the network holistically or anything like that. You would have to add some sort of analytics on top of it to do that. And rather than there being an open database like JA3, it's only internal. Of course, you can capture your own fingerprints and hold them, keep your own database if you implement this. But rather than reaching out to a community-led database, it's just based off of either the traffic that Mercury has on its GitHub or the traffic that you've collected and, I guess, cross-reference somehow. But it's important to note that even with all of this, it's still not plug and play. As I said, it's not doing any additional analytics. It's not paying attention to the context of the network or the device itself. So now we'll talk about improving on those solutions. Because of course, we're a network detection platform, and people want to, customers want to put in JA3 hashes that they see on threat reports and run them, on an hourly basis or what have you. And so, of course, we implemented JA3. You can search for JA3 hashes. You can look at the JA3 hash for TLS traffic. You can look at all the JA3 hashes for a device, for the network, et cetera. You can do all that. So we have that implemented. I also went a step further from that and implemented BrowseCap to add an additional layer of context, because the JA3 database itself just gives you back the user agents, which are not very human readable, aside from maybe being able to glance at it and say like, oh yeah, that kind of looks like a browser. Or if it just says like curl something, then like, oh yeah, that's curl. But aside from that, it's just simpler to see like, oh, browser, or oh, bot, or oh, scripting, or whatever, right? Network and device-based analytics. So this is the sort of bread and butter, the thing that separates things that we can do that are useful to things that we can do that are super useful. like that's the additional context that you need. It is important to note that all of the above here is additional context, which I think is what is missing a lot of times when JA3 or TLS fingerprinting in general is discussed. So first we'll talk about the JA3 database, very small database, easy to implement. Don't please don't query the JA3 or database directly. There's the one who set it up made it possible for you to download the whole thing, which is what we've done. So you don't have to constantly hit the website requesting and bringing it down. But so if you implement this database as we have, it adds additional context in the community. Sometimes, as you saw, it's not always correct. It can identify definitely bad sometimes. As Gary mentioned last week, it is frequent for something that used to be a JA3 that was assigned to a malware or tied to malware to then become a legitimate JA3, used by a legitimate application. But there are certainly times where if the only information that we have on it is that it's in the JA3 database as malware, and we've never seen it before any other way, then certainly that's something that's interesting at looking at. It's also better at identifying very likely benign based off of how common the user agent and JA3 pairs are to benign things, and it can be built upon further. So here's where BrowseCap comes in and why I'm not a crazy person for doing this. So again, the JA3 database collects user agents and TLS fingerprints from visitors, presumably to that site as well as others, given the numbers, but I'm not sure. Most visitors with the same hash and UA are more likely accurate. So like if they have these high counts like this, if you have a high count of hash to UA, then you can assume that's more likely accurate, unless somebody's stuffing the database, which is totally possible. But that's more likely accurate than it just seeing it one time, for example, just one off, because that means that people are clicking it with their browsers and constantly getting tracked that way. And then on the flip side, when you see at the bottom, so TrickBot, which was just submitted by abuse.ch, has a count of 1 because nobody's communicating with the website with that malware. It's picked up from an external source. And so that, as I said in the previous slide, can help us identify definitely bad, assuming that we don't plug this in and see it all over the place in the network. If that's the case, okay, probably not useful. It probably has aged out or what have you. But adding in this BrowseCap piece to it allows us to take these user agents that don't mean a whole lot, put them through BrowseCap, which is already implemented, and it'll spit out and be like, yeah, this is a browser. I've seen this before, or this is Chrome based off of this user agent, because it knows the difference between the different browsers based off of the different patterns in there. And we don't have to do additional work, right? So that much is nice. And as I said, it's a good sanity check, right? So if BrowseCap comes back with something and there's something else about the activity that tells you that it's wrong, then maybe it's not as useful. But certainly it can add, again, additional context that can help us make decisions. So here is the fun part, the network and device-based analytics that allow us to actually find interesting things in interesting ways that we'll miss out on otherwise. First example, I saw some articles and examples of malware authors using AppleScript. And AppleScript is a weird language that you can use to automate OS X. It allows you to actually hook into applications and also the Cocoa library. And obviously Cocoa library, the thing that Objective-C and Swift uses. If you've ever had the, I'll say quote unquote, pleasure of using those languages, not biased at all, don't trust me. You can hook into those, and of course they offer URL requests like anything else. And so what malware authors were doing was that they were using AppleScript to call the Cocoa library to reach out and download a file, for example. And so I wanted to know, okay, so if someone's doing something like this, I mean, you don't have to do this if you're making commodity malware. I'm sure you could, but to me, it seems like a more advanced technique. Like if you're trying to do this, that means that you're purposely targeting OS X. And it also means that you're, for some reason, you think you need to do it this way rather than, just using, I don't know, Python or something, right? To remain, under the radar. And typically it would be a good way to remain under the radar. And the reason is because Apple Secure Transport is one of those SSL libraries that, first of all, a lot of things on OS X use it. Basically, if you're developing an app using Cocoa, for example, so if you're developing an app with Swift or Objective-C, you're very likely using the same exact library. And like if you're reaching out to a net or a server over TLS, you're very likely going to have the same exact fingerprint as everything else doing the same thing, at least with the same version, et cetera. So that's important to know, and that allows you to kind of blend in as an attacker if you choose to go that route. Luckily, there is a little bit of a difference that we can identify here that can help us identify when somebody is doing something like this. So, we have this traffic, this AppleScript traffic that's using the Cocoa library to reach out to a malicious domain. If you run this this traffic through the JA3 fingerprinter, that comes back with 187 different user agents for the same hash. Of course, some have higher counts than others, but I think the highest count was like 300, and then everything else had like 50. So it's very not obvious what was happening. But again, that makes sense given like how common this fingerprint would be for the same operating system version and applications and things like that. Of course, adding BrowseCap as additional context isn't going to help you much unless you're just seeing a lot, or unless you like seeing a lot of different answers. Running this through Mercury comes back with Microsoft Outlook, which I'm not sure why. I'm assuming that Microsoft Outlook for OS X may have a similar fingerprint on some operating system version, but obviously that's not helping us here. However, if we compare it to the surrounding traffic, so again, adding the context of the network, the context of the device, then we can identify this traffic. And the way that we can do this is, so browsing traffic on OS X. So basically, if you're browsing using Apple Secure Transport, that means you're using Safari. And it's going to differ from your non-browsing traffic in a very specific way. The ALPN protocol value, you can see there's a long list on the left-hand side for Safari, is different than the ALPN protocol value for the same library, but used by not by Safari. And my assumption is that with Safari, they just wanted to support more protocols than they did with general traffic, which I suppose makes sense. Supporting HTTP 1.1 and SPDY makes sense for general applications, right? Probably doing like REST calls and stuff like that. But the important thing to notice here, and you can actually use JA3 for this since, you cannot use JA3 for this because the ALPN values are not included in the JA3 hash. So you have to specifically either hash or look at these values to tell the difference. But how you can tell whether something, or tell that something interesting is happening, is that we separate out the browsing traffic. So that's going to include traffic to ads and all of the other noisy, annoying stuff that may get in the way of us identifying malicious things. Of course, identifying malicious stuff inside browser traffic is another issue, but for this example, it's good to separate those two. And then we have our second group, which you can see on the right-hand side, which is our non-browsing traffic. And for the most part, it's stuff going to apple.com. So iTunes, you can see Apple email, things like that. And then all of a sudden we have something going out to this ad serve static domain, which is a completely different domain. We either haven't seen it on the network, or it probably is rare for the network, and certainly haven't seen it for this application, fingerprint, right? So that is something interesting to look into. And of course, we can look for other context as well. But this alone is something that we can use to alert a user to interesting traffic and malicious traffic. So proxy bypass is another interesting thing. So of course, not every proxy is created equal. There are different types of proxies. However, in this example, and the example traffic that I used, we have a host-based proxy that's basically taking all web traffic and proxying it through a proxy server. And the interesting thing here is that the proxy server is going to respond with its own extensions, right? So in addition to the client hello that we're using to create the JA3, et cetera, there is a server hello, and JA3 does have a mechanism for that. It's called JA3S. But of course, you don't have to hash it. You can just use that information and compare it. But this is the case that I meant where JA3 actually does work because the information is different enough and included by JA3. So it would work in this case. But the proxy server will respond with whatever the proxy server itself supports in terms of extensions, Cipher suites, etc. However, if you have traffic that's going out directly to the internet, then whatever server you're hitting will that will determine what the server hello is. And so the extensions, Cipher suites, etc., that it supports may and often do differ from the proxy server, which means that you'll have a unique client and server fingerprint between the proxy client and the proxy server internally that is different from the client and server fingerprint pair that you would see with the client communicating with the internet. And so what that means is that for the same client fingerprint, if we see we should see constant server fingerprints that are the same for each individual client. If we see something that's different all of a sudden, then that should be indicative of somebody bypassing the proxy. And you might be wondering how in the hell someone would do this, but we'll talk about that in a second. So again, reiterating, we should see the same J3 hash, assuming that the fingerprint is accurate. But at the very least, same TLS fingerprint, but different J3 server hash or different TLS server hash. If you add in BrowseCap, in this case, for this example, I was using curl. So we see curl and it would tell us curl and it would tell us that it's not a browser. Of course, we can just look at the user agent and tell. In this case, it's pretty clear. Mercury thought it was Microsoft OneNote. Again, not accurate or helpful in this example. And then down to bottom, we see the screenshots and how the traffic differs. So on the left-hand side, we have the traffic that includes or is hitting the proxy. And so the server hello responds with renegotiation info, EC points format. The Cipher suite is actually the same between the two, I think. Yeah. And on the right-hand side, we have an example where it's circumventing the proxy, not going to the proxy, just going directly to the server. And the server responds with renegotiation info, server name extension, EC point formats, and ALPN. And so what that means is that I guess the proxy doesn't support or doesn't care about ALPN or doesn't support ALPN. And same thing it doesn't respond back with the server name for whatever reason. But what that means is that the fingerprint for those two pieces of communication are going to be different. And so we know that we should always be seeing this fingerprint on the left-hand side. But if we see this one on the right for this individual client, then they're circumventing the proxy. And so why you might actually see this, because you're thinking, well, I should be forwarding all of my traffic through my proxy. Well, an unmanaged device, which is one of the more interesting things that we find on networks. It's so common for, networks are complicated things, right? And people punch holes in all sorts of appliances and forget about them and forget, they say, well, okay, we need this Apple TV to make an exception because it communicates in a weird way that we can't control. And so, et cetera, et cetera. And then people forget. So unmanaged device is one example. Doesn't have the proxy client on it, just reaching out to the internet. For some reason, that's okay. Unmanaged software. Let's say you're not using a client-based proxy, but you're using a proxy that is forced through a global policy, through Firefox or through Chrome or something like that, right? But then all of a sudden you have this other application that's doing its own thing. That's a separate situation or a separate possibility. And your proxy may not be doing what you think it is. So certainly there's all sorts of security tools out there that we think we set them up correctly and we did not, because again, it is not magic. It hopefully is doing what we tell it to do, but us as humans don't always tell it to do the correct thing. So it is nice to be able to identify these unmanaged things. And then it doesn't necessarily mean that they're being used actively by an attacker, but certainly they could eventually be used by an attacker, and we want to plug those holes when we can. So now JA3 evasion techniques. So some of the posts about JA3 talk about ways that you can evade detection by JA3 or TLS fingerprinting in general. And so I wanted to talk about those and then what to do about them. So the first one actually has a name, Cipher Stunting, which just means randomizing JA3 fingerprints. And the second one is spoofing JA3 fingerprints, which the example that I looked at was JA3 Transport, which is a Go application that allows you to spoof JA3 fingerprints. So Cipher Stunting. If you have a piece of malware that is randomizing its JA3 fingerprint, what that means is that if you're trying to use JA3 for detection, you can't search for known bad for sure. You can't plug in the JA3 value into the database and see what it says. You can't compare it to other JA3s one for one. You can't put it in a threat report and expect someone to search for it, right? So because it's random, it's going to be different every time potentially. Mercury, obviously, same problem. You're changing the values in the hash, so it's no longer going to be accurate. However, if you're looking at device and network-based analysis, you can very clearly tell. So at the top, we have an example of like what you would typically see for a device, right? So we have 5 different JA3 hashes for a single device. The top one, top one and the fourth one are actually all just stuff using S-channel in this example. And the last one, there always seems to be on every device, it's uncanny, the one little straggler. And it's usually because there's some sort of conditional extension or something, because in this example, it was Windows Update, and it was the same as all the other S-channel stuff. There was other Windows Update stuff in the first group and the fourth group. It's just that this one was like, it omitted an extension that all the other ones didn't, or something like that, right? So the reason why I'm bringing this up is because if you don't hash it using JA3 and you consider all the other fields and the fact that they can change, then what actually happens is you consolidate this to 3 different hashes, which one group is S-channel apps, one group is AV, and then the third group is their cloud backup software in this example. However, on the bottom, we have a device where there's malware running that's randomizing its JA3 values. And you can see there's this long tail of JA3 values. And again, I mean, we can consolidate them using, Wake's method that is not JA3 hash, but even without it, you could still see that there's very clearly a difference. So the fact, you can randomize your JA3s, but in my opinion, that makes it more noisy and more obvious. And if you only randomize it once, then it'll at least be a unique hash and something that we can, we usually refer to as characteristic, being something that is unique for a device and recurrent for a device, which is another kind of way we can go after it. But again, just simply randomizing your JA3 fingerprints is kind of assuming as the attacker that your plug and play JA3, and that should not be the case, is the argument that I'm trying to make. And then of course there's the TLS fingerprint spoofing, which I want to point out. I think there's a tendency for us to think that there is a similarity and difficulty between user agent spoofing, for example, and JA3 spoofing, and that is not at all the case. So HTTP user agents were almost fully discarded in terms of what they were used for while communicating in HTTP. Of course, some browsers or not browsers, but websites will make decisions about what you support. That's supposed to be the idea. And then, which WebKit to use, et cetera. It might tell you that your browser is not compatible, with this website or yada, yada. But aside from that, it's not going to break the protocol. Versus TLS, it actually, in order to work, it has to use all of that information, or it does potentially use all that information. So changing certain values in a TLS handshake can break the entire protocol. So it's certainly not the same as HTTP. Plus, every HTTP library that I've used, for example, Python requests or anything really, allows you to edit the HTTP user agent directly. So you can make it whatever you want. Versus TLS, editing a TLS fingerprint is a difficult process. Even the JA3 transport thing that I was talking about, they make a statement that says, okay, well, we're using this SSL library. So if there's some application that you're trying to spoof that has something that this SSL library doesn't have, we can't spoof that. Of course, if you are a APT actor, then what you would do is you would have to figure out exactly what application on what operating system version that you want to spoof is, and you would have to use the exact same library, or at least in a library that is compatible with the same features, and then compile whatever your malware is with that library. Certainly not impossible, but I would definitely put it in the APT category of who's going to be doing that, unless maybe just someone with too much time on their hands, like me. What tool did you use to download to spoof with? So if if you're downloading something that's going to spoof a fingerprint, whether it's through a script or whether it's malware that you've compiled the fingerprint into, you still have to download that somewhere. And so if that's the case, in those cases, these corner cases where it's like, all right, fine, you look like everything else, and for some reason, you look like, I would hope that you're spoofing a browser, because if you're not spoofing a browser, then we'll probably just find out that the destination is weird for that application. The browsers are the only application where you can see it go to all sorts of sites, right? But in that case, you still have to download your malware. And so I would say in those cases, if we have to catch you at a different stage of the attack, for example, the download stage of the attack, then that's what we'll do. Chrome extensions. This is probably my favorite one and most interesting one. But this came up during something that I was looking into recently. So I noticed while looking at Chrome extension traffic that the TLS fingerprints were different for the domains requested by the extension versus domains requested by the Chrome browser, not by the extension. Why? Like, what made them different? So ALPN value, which comes up a lot because you could just basically, I think because people put, their plain text protocols that they put in there, and it's one of the often exposed things, since if you have an SSL library that you want someone to build an application with, you probably want to support several different protocols and let them make a decision about which ones. That's just an assumption, but that's probably why it comes up a lot. But it is what I call one of the conditional extensions, although I never looked into why until recently. But again, conditional extensions are just those that are sometimes present for the same client. So same browser, sometimes the ALPN is there, sometimes the ALPN is not, etc. But why? So that's what I looked into. And it looks like there are a number of extension values, depending on the SSL library, that are cached. And Chrome extensions, for whatever reason, don't seem to have access to or choose to use that same caching mechanism that the browser uses. And if you want to look at the code, the link is there. This will be posted, I think, on YouTube later, so you don't have to write it down now. But quick, take a screenshot if you feel like looking through Go code. But that's you can see where the cache is and where it's trying to make that decision about whether to use the cache or to keep it in cache. And so what that created in this scenario was that we had the traffic in question. So Office 365 followed by Pastebin, followed by Ledger Wallet. The extension traffic was the Pastebin and Ledger Wallet traffic. I noticed that the Office 365 did not have an ALPN, and the extension traffic, or the Pastebin and the Ledger Wallet did. And the Office 365 was requested obviously earlier between browser startup and when the traffic in question happened. And so that's why, at least that seems to be the case, why no ALPN was requested a second time, because it already knew what protocols the server supported. So it didn't have to ask again, it was held in cache. However, there's a later request for Ledger Wallet, presumably because the user did legitimately use the site, that did not, or sorry, still included the ALPN, which seems to indicate that it was not cached. So we see two different things here, that if something is cached, it'll be, or it won't use the ALPN a second time, and then it won't be cached if it's used by the Chrome extension and not in normal browsing traffic. And so, is this something that you can use to just look at a large swath of traffic? No, but if you have a smaller set of interesting traffic, you can use it to potentially separate out, what are the things that were the extension, what are the things that weren't the extension, based off of what else that device has done, or what else, I guess, specifically that application, in this case, the browser, has done on that device, and whether we think the ALPN should be there or not, which again, it's just indicative of us understanding and using how applications actually work on the network to identify, what they're doing just using the network traffic alone. So wrapping up everything, I know we went through a lot. I appreciate everybody sticking around and listening. So one of the big takeaways is people that are kind of spreading FUD and doom and gloom about TLS 1.3, please stop. Certainly, it's not that there's, we shouldn't make any considerations about what to do in certain situations or whatnot, but stop saying that things are currently encrypted, the client is currently encrypted. It is not. Stop saying that the ESNI is something that is a huge problem right now. It is not. it's important to take away that fingerprinting works with context. So certainly, I imagine you can get some use out of just using JA3, but in my experience, fingerprinting without context doesn't add as much value, which brings me to don't settle for plug and play JA3 or plug and play any sort of fingerprinting method. And then also take away, we can find some pretty cool stuff in some pretty cool ways just using the plain text traffic that's available in the TLS client hello and server hello. Now we'll open up for Q&A. If I don't get to your question, or if you are too shy to ask questions, which I totally understand, you can tweet at me, Sonic the Hexhog, on Twitter. That's a good way to follow up. If you want to grab a beer and talk about it too, that's totally fine. I love talking about this stuff. Very interested. And that said, if anyone does see any traffic with encrypted client hello, send it to me. I want to see it. The second I find it, I'll definitely share it as well. But yeah, so Q&A, Will, if you have any.
Yeah, thanks, Troy. Fascinating stuff there. We do have a couple of questions that were entered in during the course of the presentation. If anybody else has any questions, I would encourage you to go ahead and type them in to the Q&A section of the Zoom interface at this point. But we have a question from Sunil here, and he asks, have you used any of these techniques to actually find anything malicious?
Yeah, so I should say, before we even started looking into what is currently considered to be TLS fingerprinting, so meaning JA3, et cetera, we were already using the list of Cipher suites and extensions to kind of glean information, and it's already baked into a lot of our models in that sense. The Ledger Wallet example was something that I wrote a blog post about maybe a month or so back that was sort of overshadowed by some Twitter hack that had happened at the time, I think. But yeah, so that was an example of something actually malicious and interesting that was found using these methods. And then while, Gary I'm constantly working with Gary and the rest of the team to help them add additional context with the research that's not yet implemented, which I guess these days has been implemented, but back when it wasn't. So we've been using this for quite some time. It's just a matter of the level of implementation.
Okay, super. Let's see. We also have an earlier question from George, and he's asking, is there anything I can do to eliminate the false positives?
Yeah, so I'm assuming you mean like with J3 or Cisco Mercury or something like that. So the way, basically, it's the context that I've been talking about, right? So you would have to look at a larger swath of traffic, like for a device, right? So rather than say, is this JA3 bad? Is this JA3 good? Look at the JA3s over a period of time for a single device, or look at the JA3 hashes over a period of time for the entire network, et cetera. And then compare that hash to those, see how common it is. Because for example, like if you get a hit on a hash that was in a threat report, but you're worried it might be a false positive, if you see that hit that is ubiquitous across everything, it's going to all sorts of different websites, then that's going to give you the additional context that you need. Maybe not quite enough, but at least additional context to say, okay, I think something else is going on here, unless I think every device on my network is hosed. So that is definitely helpful. If you have a way to keep around the additional information aside from just what's in the J3, that can also be helpful. But I understand that that's not always extraordinarily scalable with open source tools currently. But I would say at least right now with J3, the best way to do it, and the way that I've also heard some of my colleagues at other places doing it, is essentially looking at the J3 collection over the course of, or over the entire network or over the device itself, and seeing how common, uncommon, or what context or what the destinations are, and all of that extra context that can tell you maybe this is a legitimate application or not.
All righty, good stuff. And finally, we do have a third question here from Perry. And Perry's question is, how can you implement a complex set of rules like the Chrome extension detection.
Okay, so what I did, so we have the ability with our query language to basically hone in on some amount of traffic and then look at surrounding traffic for that device, and then make decisions like that. So it was basically just a language that allows me to do that, right? So in a general situation, well, I don't know what the performance of like Python or something would be, but let's say for the sake of argument that you're using Python and like some sort of API with some tool that you're using, or maybe Bro. I'm not too familiar with Bro and how you would do it, but you would basically have to find the traffic that you're interested in and then move out from there for that device, and then look to see, oh, are there other ALPN values or not for these domains? And then say, okay, these are the ones with them. These are the ones without. These are the ones where this application on this device has never seen it. These are the ones where it did see it at one time. Now it's not seeing it, which is indicative of it being cached. So like that's basically how you'd have to do it, like group bys and things like that. Yeah, so which again, I understand is not always a super scalable thing. It's definitely not something that I would, again, apply to like a huge PCAP of traffic or like a whole hour of an entire network or something like that. You do have to hone in on something interesting first and then ask those questions after the fact. I imagine to be scalable. Maybe there's some supercomputer stuff out there that I don't know about, but in my experience.
Well, all righty. So it looks like we're coming up against our time stop here. I want to thank everyone that has attended today. I would encourage you to check out Awake Security's YouTube channel for additional recordings of our webinars. Do visit us at awakesecurity.com. You'll find some fascinating subjects in the blog section that Troy and the rest of the research team have produced there for you. And with that, we'll go ahead and end the webinar, and we hope to see you again next time with Awake Security.